Alright, so last time we started talking about how to develop fragility functions. I know I have computer issues, so I have to explain everything on the board, but it was good that you know the knowledge and the science behind what we're gonna do right now. So, do you guys remember what was the first step to develop fragility analysis? If you guys remember, we have to have a table. This table should have all the components in the buildings, and we have somehow to find what is the damaging elevation of these components, right? So remind me when I get to the computer to start record the screen, okay? If I forgot. So I have to have a table, and this table somehow how to have the damaging elevation of all the components. This damaging elevation can be mean and standard deviation, can be an upper and lower bound, and then from the upper and lower bound we can somehow find the mean and standard deviation. Same thing with the flood duration. It has to have an upper and lower bound for the flood duration that the component can get damaged in. Same thing with the replacement cost. We need to find an upper and lower bound of the replacement cost of each component. And then we use this upper and lower bound to find out what is the mean and the standard deviation to replace each component, okay? All right, so before you develop the MATLAB code, maybe I have to spend a week, a month to develop these components. So the way that I have done it, if you guys remember, we have 15 building archetypes, right? The one that I talked to you about. So like if I go back here, I will find out that I have archetype 1 on up to archetype 15.
Cool.
Okay, thank you. All right, let's go here, record. Oh. All right, so I have the 15 building archetypes here, and right now I'm gonna use archetype 3 as an example. So if I open archetype 3, so the way that I did it, I made a rivet model of a typical 2-story building in the US, this rivet model. And this is basically the rivet model that I have for this building, like a typical 2-story building in the US. And I developed the architectural design. I know it's not maybe the best, but I believe it has most of the components that we need to develop this archetype. So it has like a garage, like the kitchen, the living room, laundry room, office, bathroom, and then the second story is the one that has the other rooms inside this house. And then based on this rivet model, I was able to identify what kind of component that this building is gonna have. I did the same thing with every building archetype, from archetype 1 to archetype 15. If in a hospital, a school, I have a very, very detailed rivet model so that I can have a representation of all the possible components that can be inside this building. I know that this building might not represent all the 2-story buildings inside the US, but the thing is, we have uncertainties. Like we have upper and lower bounds of everything. And let's say, if a building that has 5 bedrooms or 7 bedrooms in the second story, but the thing is, the damaging elevation for all the furniture is going to be the same, like bedroom 1, bedroom 2, bedroom 3. So our fragilities are be representative of any building that is going to be that is going to have like 2-story archetype. Okay, so this is my archetype. Start counting all the possible components, and I made an Excel sheet for all these components here. All right, here is the Excel sheet. So let's see what does this Excel sheet have. This Excel sheet has like all the possible components that I got from the rivet file. So you'll find out that I was able to list maybe over 100 components. Like look here, I have like the crawl space base insulation, the garage drywalls, garage cabinets, flooring insulation, garage electrical outlets, every component. And then you will have at some point, you will find refrigerators, stove, washer, speakers, dishwashers, kitchen, upper cabinet, lower cabinet, and even the painting, the drywalls. But I have to divide the painting and drywalls because they are linear element. I have to divide them into levels. Like if the drywall got the first 2 or 3 feet from the drywall, I put them, because if you guys remember, I have to group these components by their damage state. So the thing is, if the water is here, that means it's a damage state 2 or something. But if the water is here, it's damage state 3. So I have to divide the drywall because it's a linear component and it extends from damage state 2 to damage state 3. So if you find out here, I have most of the linear component or the vertical components, like where the drywall, okay, here drywall damage state 2, and you will find drywall in damage state 3. External wall sheathing, the walls from the outside and the cladding, there is part damage state 2 and part is damage state 3 because it's a lengthy component, it's a vertical component, so we have to include it in part in damage state 2 and part in damage state 3. And somehow I was able to list all the components. Let's see how many components that we have here. We have 94 components. And if you see, I give them like light colors, like from the light gray to the darker gray. The more it gets grayer, the more the damage state is gonna get higher. So I group them, like the first group that we have here, look here, I have all these groups are damage state 0. And then the next group is damage state 1. The next group is damage state 2, damage state 3. So I listed them based on their group or their contribution to each damage state. All right, so I finished listing all the components. The next part is to find the minimum and the maximum damaging elevation for each one of these components, and the minimum and the maximum damaging duration for each one of these components. And here we use the knowledge-based models and also some parts from the literature to find out how people, there's some tests that has been done on these components to find what is the damaging elevation of these components. So I listed them, minimum to maximum, and then if you guys remember, we got the mean by this plus this over 2, and we got the standard deviation by this, the maximum minus the minimum over 4. So that's what we discussed last time. Same thing with the duration. All right, and I described each one of them. Like, what is this component? This is 5 are usually above the baseboard. This depends on the manufacturer, but this is the mean value. So I added a little bit of description to guide me about the damaging elevation of these components, okay? All right, so I had everything in place, and then I want to know what is the unit price of each component. So if you look here, you'll find I have a minimum unit price and a maximum unit price. And let's say, okay, like let's say the refrigerator, go all the way here. Like I said that the minimum unit price is 450 and the maximum is 3,000, okay? All right, so maybe the prices right now is different, but that's what I had at that time 5 years ago. Okay, so here's the, yeah, the unit price. So I have the maximum, the minimum, and the maximum. I get the mean, I get the standard deviation, and I got the number of units. What does that mean? The thing is, like something like the drywall, I have the unit price by square foot. So I have to find what is the total square footage of the drywalls that I need. So, or maybe, so some of them you will find, like if we are talking about refrigerator, we will find that the number of units is 1. But if we're talking about elements that are linear foot, like pipes, so I have how many linear footage. If it's a flooring, how many square footage. If it's a drywall, how many square footage. So I have to use Rivet to find out what is these footages look like. All right, and once I found how many units that I have, I can find what is the minimum price and what's the maximum price by multiplying the unit price by the total quantity that I have. Like if I have pipes that is like, let's say 100 foot, and the price per 1 linear foot is like $10. So 100 by 10 is $1,000, the total cost of the pipes. And definitely I have to include everything in the linear footage, like how much labor, how much material, and all these stuff. Okay, and then once I found the minimum and the maximum replacement or the maximum cost of the component, I was able to get the mean and the standard deviation using the same way. The minimum plus the maximum over 2, you get the mean. The maximum minus the minimum over 4, you get the standard deviation. Okay. So, and then I have some description because I had to, like all this information, I had to go online to find the replacement cost of each component. Like I used many estimators, many websites. So that's what I was able to get from online. Like this is the average per square footage, and I got this from Home Advisor website, and I got this from a different website. So I have to find all these things by myself. All right, so, and at the end, I want to get information at the damage estate level. So how did I do this? The thing is, I found the mean replacement cost of all the components in this damage estate by summing all the means that we have here. So I was able to get mean damage estate loss, okay? And then I was able to get the mean damage estate loss cumulative mean. Like let's say I'm in damage estate 3, so it's gonna be damage estate 1 plus damage estate 2 plus damage estate 3. So I get one number 4. If I'm in damage estate 3, that means I'm losing all these 1, 2, and 3. But if I'm in damage estate 1, they are all the same. If damage estate 2, so this plus this is gonna give you this number. And then I got the standard deviation loss. And by the way, the standard deviation, we don't sum like standard deviation 1, 2, and 3. As far as I remember, you take the square root of the sum of the standard deviations. Like let's say, yeah, this one, the standard deviation is a square. Like for the standard deviation, if you want to get the standard deviation of a group of components, you don't say it's the standard deviation of 1 plus 2 plus 3. You have to square 1, square 2, square 3, and take the sum of the squares of all the standard deviation. Okay, so, and then I was able to get ratio. What is the replacement cost ratio? The replacement cost ratio is equal to this mean over the total replacement cost of the building. So you know what's the contribution of this damage estate to the total building replacement cost. So you have this like 1,600. So you have this like 1,600 and the total replacement cost of the building 500,000. So you divide the 1,600, the 16,000 over the 1 million, and then you will find out that is 0.04, it's a 4%. And damage estate 2 is 11%, damage estate 3, 20%. And the sum of all of these should make the 100% of the replacement cost of the building. Do you guys got that? So I'm trying to explain to you what I have in this Excel sheet, because this is gonna be our input to the fragility analysis. Because you can't develop fragility without knowing information about the components, right? Okay. So, and then I believe the last column is the cumulative replacement cost. Like you will take this plus this is gonna be 14, and at the end you are gonna have like the 100% of the building replacement cost. All right, so that is the components. So let's go how we are gonna make MATLAB read this Excel sheet. All right, so the first thing, I always, when I start any MATLAB code, I always like close everything, clear all the data, clear everything. So if I'm running other codes, so it clears all the inputs that I have from other codes, so I can start from scratch. All right, then I want to read the Excel file. Just make sure that you have a folder. This folder has the Excel sheet that you have, and also have this MATLAB code. Like you are gonna start the MATLAB code file, new MATLAB folder. Like you will go from here and then make like new script. Once you hit a new script, save it in the same location or in the same destination that has the same Excel sheet, so that when I ask MATLAB to read an Excel file, so we can find it in the same folder. If it's not in the same folder, it's not gonna read it. And then I say XLS read, like read an Excel file, and this is the name of the Excel file, building components for archetype 3, and read sheet number 2, because this is the sheet that I have the data. If you only have one sheet, maybe you can escape sheet 2. I mean, if it's only gonna get to this sheet, but I have multiple sheets. So we need to read sheet number 2. All right, once you run this, A is gonna show up here in the workspace. If you open A, you will find all the data in the Excel sheet here. Can you see? This is all the data in the Excel sheet. And by the way, these nans are the fields that I have description, like words. MATLAB doesn't read words, so it puts nan, and it only reads the number. And by the way, the mean and the standard deviation was in column number 5. Like the mean was in column number 5, and the standard deviation was in column number 6. Like let's go here. Column 1, 2, go all the way back. 1, 2, 3, 4, 5. Mean was number 5, standard deviation was number 6. So if I go to the MATLAB code, I will find out that the mean was in column number 5, and the standard deviation was in column number 6, all right? So, and actually that's the two most important column in this Excel sheet, because that's how we're gonna build our fragility, based on these two columns, all right? So, I read the Excel file, and then I want to extract the most important columns. I wanna develop a fragility function based on the damage of the components, so I need the damaging elevation of each component, and I also wanna develop loss function that can reflect how much money I'm gonna lose, so I also need the replacement cost, the mean and the standard deviation. So what I'm gonna do right now, I'm going to extract or take these two columns out of the whole Excel sheet. So I took the mean depths and the standard deviation, so I put mu and sigma, and I said that mu and sigma are in Excel or in data A, like the 2D, like this data A, and it's in column 5 and column 6. So that means I'm asking MATLAB extract all the information in all the rows at column 5. Like for each row, extract column number 5. These two dots, that means for each row, like all the rows. Like when I put these two dots here, that means not from row 1. Like if I put 1 here rather than this, it's gonna extract this number. If I put 6, it's gonna extract this number. But once I put this two dots, that means for every row, extract the information in column number 5. And same thing, extract all the information in column number 6. And I call them mu and sigma. These are the two columns that are important to me. All right, you guys got that? Okay. All right, I did the same thing with the replacement cost. The replacement cost for the components was in column number 20 and column number 21. Let's go here in the Excel, in this column 20. That's where the total replacement cost and the sigma. So if I go to my Excel sheet, you will find them here, the minimum, the mean, and the standard deviation, these two, okay? All right, let's get back. All right, I extracted these 4, and then I start to define things that is gonna help me in developing the fragility. If you guys remember, when I developed the fragility, I have depth here, right? Do you guys remember? We are gonna generate 1,000 simulation, and at each of flood depths, let's say 1, 2, 3, up to 10 meter, I wanna find out, is the flood depth is 10 meter, how many components are gonna be damaged? Is the flood depth is 1 meter? But the thing is, that's what you are gonna decide. If it's every 1 meter, or every 1 centimeter, or every 1 millimeter. So what I did here, I defined depths D, and this D is gonna be equal from 0 up to 10 meter, and the set is every centimeter. Like I said, I want depth D start from 0 up to 10, and I will go steps every 0.01 meter. So right now, I already defined what is the flood depths that I'm interested to investigate. Okay, that's verse number 1. And the length of these flood depths is the length of this column. So basically, if you want to find out, it's going to be 10 by 10. It's going to be 100. Actually, no, it's 10 by 100. It's 1,000 step. So I'm going to go 1,000 step, 0.01, 0.02, until I get to 1. That's 100 step. And I'm going to do it 10 times. So that means it's a 1,000 step. That's the length of this column, right? And think about it, MATLAB, we are dealing with matrices and vectors. So once I made this, this is a vector. A is a matrix. This A is a matrix. Has like columns and has rows. Like all these are rows and these are columns. But right now I take one column or two columns out of this matrix. And this is the matrix of these. So I'm defining the matrices that I'm gonna deal with. And the length of this matrix is the, like I said, n depths is the length, like how many depths that I'm dealing with is the length of this vector. And how many components that I have is the length of a matrix. This A matrix has 60 or 94 components. So the length of A is the number of components that I have. Like if I open A, and every row, that means the length of A, so I have 94 components. And the number of simulation, if you guys remember, I told you, we are gonna have a Monte Carlo simulation. I'm gonna explain what it's gonna do actually. I told you we're gonna have the mean and standard deviation, and we are gonna give it to a black box, and this black box is gonna generate 1,000 elevation of the component. I told you it's a reverse process from what we do in the field. Like in the field or in the lab, you get a 1,000 concrete block. That's what you give it. You get 1,000, you test them, you get 1,000 number, and then you take the mean and standard deviation. Right now we have mean and standard deviation, these two numbers, and we need to get 1,000 number. So we give it to a black box that I'm gonna show you what is this black box is, and it's gonna generate random 1,000 number. If you plot them, it's gonna give you a normal distribution with the mean that we have from here and the standard deviation that we have from here, okay? So that's the process that we're gonna do. But the thing is, you have to tell MATLAB first, how many simulation do you want? Do you want 100 simulation? Do you want 1,000? Do you want 10,000? By the way, the more simulation that you have, the better, because it's gonna increase the accuracy, but it's gonna take much more time to run the analysis, okay? All right, so I have here, the simulation is 1,000, and the number of damages state is gonna be 5. You can make them 4, but you have to redesign the whole fragility. Sometime, like after I finished this research was 2 years, the sponsor that we are doing this research for decided that we need to decrease the fragilities from 5 damage states to 3 damage states. So we have to redesign the whole thing. Even the Excel sheet, rather than having 5 groups, we're gonna have 3 groups. So some components joined, like damage state 2 got joined with damage state 3, damage state 4 got joined with damage state 5, something like that, okay? But I decided here how many, the number of damage state that I have. All right, and then I ran this part. Okay, that's until here. Then I want to generate the samples. I told you that we are gonna have a black box that we are gonna give it the mean and standard deviation is gonna generate 1,000 variable. So what I wanna generate is, I wanna generate failure depths for the components and replacement cost for the components. So, and this is gonna be a table, if you guys remember from last time. It's gonna be something like this. I want a table like this. And this table is gonna have, here is the number of simulation. Like here, like it's gonna be 1, 2, 3, up to 1,000 simulation. And I want to have the components, like let's say it's component number 1, component 1, component 2, until component number n. Let's say I have 94 component, so I have here from component 1 up to component n. And let's say component 1 is the refrigerator. Like the refrigerator is gonna damage, maybe you're gonna have, for example, 0.2, 0.6, 0.5, 0.9, until 1,000 simulation. Same thing for the dryer, same thing for the washer, same thing for the electrical outlets. You're gonna have this for every component. So I'm redefining, I'm preparing the matrix. It's always better for MATLAB to tell him what you are gonna do next. You tell him, oh, I want you to create an empty matrix, all zeros, has a length of 1,000 and a width of the number of components. That's what I did here. Just prepare a matrix, because I'm gonna need it right now. Prepare a matrix that has zeros, and it's the number of rows is the number of simulation, and the number of columns is the number of components. So the rows is the number of simulations, and the columns is the number of components. And all of it 0, and I'm gonna fill it in a few minutes. I'm gonna put numbers in it, but just prepare it for now. Okay, and do the same thing for the replacement cost. Prepare a matrix that has the number of simulation, and here is gonna be the replacement cost of each component, okay? So one of them is gonna have the damaging depths, and one of them is gonna have the replacement cost. And if you are gonna develop a 3D fragility, I need to have a third one that has the damaging duration of each component. And the size of these matrices is the number of simulations by the number of components. Then we will get to the black box, the Monte Carlo simulation, the generation of the samples. So for the replacement cost and look what I did. I said for, I'm gonna create a for loop. For loop is, the thing is we don't have one single component. So for loop is doing the process for multiple times. So the for loop, you say for component number 1, run this thing, and once you finish, go again to component number 2, and go again to component number 3, until component number k, or n components, like k is equal to 1 up to n components. Like from component number 1 up to n. Do the same process. Okay, let's see what is gonna happen. Find the replacement cost for k. This k can be 1, 2, 3, up to n components. And this replacement cost is equal to abs mean the absolute. Like I don't want, like when I told you, like if I give a Monte Carlo simulation, mean and standard deviation, and I told the MATLAB to generate the sample, is gonna generate positive and negative value. So the thing is, to get rid of the negative value, we take the absolute. So I put absolute outside. So any negative number is gonna be positive. And generate something is called normRand. normRand is a function in MATLAB that generate random numbers normally distributed if you give it the mean and the standard deviation. Okay? So if you give this the mean, or I give it the mean right now, I give the mean replacement cost and the standard deviation of the replacement cost. And I told the MATLAB to develop a 1000 simulation because I give it also the number of simulations. So normRand is a function that you can give it the mean, the standard deviation, and the number of simulation, and it's gonna generate 1000 simulation. All right? So once this is done, let's see what we have here. Like once you said, like run this section, once you run it, let's see what we have in the replacement cost. So it's gonna be replacement cost here. See? If I go down, it's gonna go down all the way up to 1000 because we are generating 1000 simulation. Every one of these is the replacement cost of each component number 1, component number 2, and that's the replacement cost. They are all different, but they are close. And if you take the mean of these, it's gonna give you this mean that we have from the table, like the mean that we already given to MATLAB. And if you take the standard deviation, it's gonna be the same thing. So let's go all the way down. So you'll find out that we have 1000 number, and each column is a component. Like here's component number 1, and I believe we have 94 components up to component number 94. So right now we have 1000 number of the replacement cost of each fridge. Do you guys remember I told you, you go to the lab with 1000 sample, you break them, you get 1000 number, and then you get the mean and the standard deviation. We did the reverse thing. We give the MATLAB mean and standard deviation and give us 1000 number, all right? Okay, and we are gonna do the same thing with the failure depth. The failure depth of every component, I want you to generate an absolute random variable with mean and standard deviation of the one that I gave it to you and what was 1000 simulation. And then if you want to plot a histogram to show you the data, the samples that you generate, like here I wanna see like block component number 63, show me a histogram of the 1000 number. Like it's gonna show you, because I ran this code before I come, so that we don't have to wait until it shows. Like if you look, when I plot this data, it basically like a normal distribution. Any component that you're gonna plot is gonna show like this. Like let's say I wanna see component number 1. I'm gonna change this from component number 63, and I'm gonna rerun this histogram. So it's gonna be something like this, something different, but it's still normal distribution. And actually you can change this maybe to 10 so that you can see it better. Something like this. That's normal distribution. If you want to make it much more, 10, like 20 groups, so you group the data by 20, so it's going to show you something like this. All right?
Yep.
So right now, I was able from two numbers, mean and standard deviation, generate 1,000 simulation, and when I got their mean and the standard deviation, it's going to give me the same, maybe not the same, but very close number to the mean and the standard deviation that I got. And when you plot them, they are going to show you normal distribution. If you make the function not norm rand, I told you norm rand is going to generate normal distribution. There's something for log normal. It's called log norm rand. If you want to develop random simulation or random samples that follows log normal distribution, and there is uniform. So all these functions is outside. Because sometimes in your research you will find that people has like distributions that are normal, and you want to generate samples. So if it says that it's a uniform distribution, so you have to develop URAND. If there's normal, norm rand. If it's log norm rand. And by the way, if you want to find the characteristic of this function, you can click on it. Like you can come here and click here, and you say open norm rand, and it's going to tell you more about this function. Let's say help on norm rand. So it's going to open something like this. And it's gonna have more explanation about the function. I don't know why it doesn't load. Okay, so it's gonna tell you what you should do, what you should put here, and what is the different ways that you can write it. So you can understand more about this function, and it's gonna give you some examples how to anything on MATLAB. Like if you stuck with something, click help, and it's gonna show you how to do this stuff. All right. So right now, I'm gonna open the failure depth, the 1,000 simulation of the failure depths that we have. Can you see? Right now I have 1,000 simulation of component number 1. All these component number 1 component, and that's the failure depth of the component. So component number 1 can have a failure depth of 0.18, 0.34, 0.18, 0.33, 0.28. So we have a 1,000 number. If you take their mean, they're gonna give you the same mean that we have. If you take your standard deviation, it's gonna give you the same standard deviation. All right. The next step is I want to see what is gonna happen to all these components, the 94, along with their simulation, their 1,000 simulation, and they got exposed to a flood depth of 0.1 or 0.2 or 0.3. So I'm gonna take this one flood depth by one flood depth, and that's why I have to make a for loop, because I'm gonna repeat things, okay? So look at this, what is gonna happen next. In this section of the code, I want to do a spatial component damage, and I wanna find the a 3D matrix that has the failure of each component. This is the 3D matrix, has I, J, K. In I is the number of simulation, J is the number of flood depths, K is the component. So I wanna find out for every component, for every flood depth, for each simulation, is the component is damaged or not. Look at this. I want to find for component 1, at simulation number 1, for flood depth 0.01, if the component is damaged or not. So since it's a 3 things, that means it's a 3D matrix. So you're gonna have like a 3D matrix. The X is gonna be the number of simulation, Y is gonna be the depth, J is gonna be the number, K, the number 3 is gonna be the number of components. And each number is this 3D matrix is gonna have 0 or 1. That means if component number 1, for simulation number 1, if got exposed to flood depth 0.01, is it damaged or not damaged? Then you are gonna, if it's damaged, we are gonna put 1. If it's not damaged, we are gonna put 0. Do the same thing for component number 1, for simulation number 1, if it got exposed to flood depths 0.02, 0.0. Once we finish all the flood depths, we're gonna go check all the simulation for component number 1. Like simulation number 1, simulation number 2, 3, 4. Once we finish all the simulation, we go to the next component, okay? All right, so here's 3 for loops, and each for loop, I'm saying for each simulation, for each flood depth for each component if the flood depth DJ is, if you guys go up there, D here is the flood depth vector, and the flood depth vector have around 1000 number and start from 0 to 10. I want to check for each flood depths 0, 0.01, 0.02, 0.03, one by one, and each one I give them a number J. And I'm saying if the flood depths DJ is more than the failure depths of the component, what is going to happen? Is it damage or not damage? If the flood depths more than the resistance of the component, or the flood depth resistance of the component, like let's see my fridge is here and my flood depth is here, so it's gonna pass, it's not gonna fail. But if my depth is here and my component is here, that means it's gonna fail. If it fails, put 1 in this matrix. And then you are gonna do all this for all the components, for all the flood depths, for all the simulations. So you are gonna generate this 3D function, okay? Do you guys understand this? All right. All right, but right now I know if the component is failed or not, but I don't know what is the probability of failure, right? Do you guys remember how can I get the probability of failure?
So it is the summation of this value on the number of total simulation.
Exactly. It is the number of fails over the total number of simulations. So if you guys remember, so all what I'm interested in here, I want to find for each component of these, how many fails do they have at each flood depth compared or over the total number of simulations. If you find this, you will find what is the probability of failure. And when we do this, it's gonna convert it from 3D matrix to 2D matrix. Why? The thing is, this 3D matrix has the number of simulations, right? But right now, we wanna find out what is the probability of failure, one single number, at each flood depth for each component. So that's why we are making 1000 simulations so that we can get one number, which is the probability of failure. Like for each component, I apply, I have 10,000 simulation, and for each flood depth, I found that from out of these 1000 simulation, there is like 400 fail and 600 pass. So 400 over 1000, that's the probability of failure. So look what I did first. I came here and I said, for each component, start counting for each flood depths, and I start the counter, the failure counter by 0, because I want to count, I want to check them one by one. And for I equal 1 to I equal the number of simulation, if the 3D matrix has number more than 0, which is the 1, I can say if dm is equal to 1, 1. Like if you want to change this, you can put this in a different way. Like I put if the matrix has number more than 0, that means 1. I only have 0 or 1. Or you can say if it's equal to 1. But if we want to put condition here, we put equal, 2 equals. Okay. But anyway, so I'm saying if it's equal to 1, that means it's a fail. Increase this counter. So it's gonna be 0 plus 1, and then end, and then check. Simulation number 2, simulation number 3, simulation number 4. Keep looping until it finishes the 1000 simulation. And once it's finished, here is gonna do this. What is this? The probability of failure. So look at the sequence. I said I want to go here and check the 1000 simulation. Do this condition. If the component is damaged, increase the counter. And once it's finished, calculate the probability of failure. And by the way, when it calculates the probability of failure, I will go to the next flood depth, because the probability of failure is at each flood depth. Like here, maybe the probability of failure is 0.1, but here is the probability of failure 0.2. So I check what is going to happen every flood depth. Okay? So look at this. The probability of failure is for each component, because the components are k, and for each flood depth. And once you finish this, go to the next flood depth. So flood depth, the next one is 2 meters. You are gonna do this and check the failure at 2 meters. And once you finish, go to the next flood depth. And once you finish all the flood depths, go to the next component. You see how many loops are inside each other? Okay. So here I calculated the probability of failure, and I also calculated the replacement cost. How did I calculate the replacement cost? So, if you guys, I'm not sure, I believe I explained it before, like the replacement cost, I told you, I believe before, that is equal to the probability of failure of the component multiplying by the total replacement cost of the component. Let's say I have this disk, it's like $1,000, okay? And I told you it has a probability of failure of 40%. So what is the estimate of this disk to be damaged or to lose money in this disk? It's 0.4, its probability of failure by its total value. But if I told you this disk has a probability of failure of 0.1, so that means it's 0.1 multiplied by 1,000. So that's what I did here exactly. So I multiplied the probability of failure for a specific component at a specific flood depth by the replacement cost of the component, so to get the total replacement cost. And I did the same thing with, I got the mean of this value and the standard deviation of this value. Because right now, I have this for, if you guys remember, this replacement cost is 1,000 number, right? Like, if you guys remember, I generated 1,000 simulation, and the thing is, I multiplied the probability of failure by 1,000 number. Like this one, this thing is not one number. It's like a vector, like this, and has up to 1,000 number, the replacement cost of the component, because we have a mean and standard deviation. Then after I multiplied the probability of failure by this 1,000 number, I have another vector with 1,000 number. So I want a single number for the replacement cost. So I take the mean and the sigma of this 1,000 vector, so I can get the mean replacement cost. So I shifted from the mean and the standard deviation of the total replacement cost to the mean and the standard deviation of the replacement cost, okay? Because the thing is, like, let's say, as I told you, this component has an average, like mean total value, like the total value of this is 1,000, but this 1,000 is a mean. Maybe it can be 1,100, 1,200, 900, that's a mean, it has a standard deviation. But I also want to know what is the mean replacement cost and what is the mean standard deviation. So that's what I did here. I got the mean and the standard deviation of the replacement cost of the component. Then the next part is to plot what we have here. Look at this. I'm plotting right now on x-axis, like I said, create a figure 2, because figure 1 was the histogram. I want to create figure 2. In this figure 2, put on x-axis the flood depth, and put on y-axis the probability of failure of the components, and I want to plot all the components. Because I put K here, and focus, look here. I still have these plots is in the for loop. And the for loop that ended, look, this for loop that has the flood depth ended here. And this for loop ended here. This for loop didn't end yet. So all this is still in the for loop. So I want for each component to plot a figure. And by the way, they all are gonna be plotted in the same figure. Like this, once you finish, because I'm still saying figure 2, but you know, if I put here figure K, so it's gonna create many figures. But here I said in the same figure, plot this, and once it loops, in figure 2 is gonna plot on top of it. If you run this simulation on your computer, you are gonna see them, they're getting plotted one by one in the same figure. All right, so once you plot them, you are gonna have something like this. Because we have 94 components, and that's all the failures or all the fragilities of the component. On x-axis, we have the probability of failure. On y-axis, we have the flood depth, and this is all the components that we have. And that makes sense to me, because I have components that has damaging depths here, components. Oh, okay, let me ask you a question. Why there is concentration of many curves here, and here there's not much curves, and you come here, there's a lot of curves? And here, there's like a few curves on their own. Like why they are not all of them in one region?
Because there are different components and they
Not only different components, there is something.
structural component and the non-structural component.
Different probability, right?
No, remember we have two stories,
Yeah,
right?
yeah, because-
So we have component in like 1 meter and a bunch of mini component at 3 meters. So if you look here, most of these components are in the components in the first floor at 1 meter flood depth. And most of these components, when you go after 3 meter to the second story, there is a lots of furniture and lots of appliances and lots of things on this story, so you'll find a lot of them here. So that's why if you, and I believe if I have 5 stories, so you will find a bunch of components concentrated at a bunch of elevation and a bunch of elevation and a bunch of elevation, because as the waters keep going up, more components are gonna get damaged. Because here, there's no components here in the 3 meter, not much as here, so there's a lot of them here. Maybe lots of mechanical and stuff, because this is a mechanical building, but I'm talking about residential building, so there's not much of components here. So that's the reason. If I'm having a 1-story building, I'm not gonna have this pattern. I'm gonna have all the components concentrated here, and there's not much here. Okay, so that's the fragility curves of the components. The next step, I wanna plot. Here I'm plotting like one curve to show the losses. Look at this. I'm plotting the depths with the mean replacement cost. Okay, look here. This curves, not fragility curves. This is when we multiply the probability of failure with the replacement cost. And by the way, I'm not talking about the shading, I'm talking about the curves that has the color. I'm gonna tell you what is the shading is. But this is the replacement cost of each component in dollar value. Okay, so I'm plotting them one by one. There's some components that are cheap, some components that are expensive. So I'm plotting depth with the mean replacement cost. And I asked MATLAB to shade the standard deviation of the replacement cost on top of the mean, because this is the mean. And this shading showing you how does the standard deviation look like. Okay, definitely the more that you lose, the more the standard deviation is, until you go to the maximum value and the standard deviation get to be constant. Okay. All right, so that is the replacement cost, and all what I'm doing here, I'm just putting labels. I'm naming the x-axis flood depth, so that when you plot this, you'll find here that this is flood depth, and here I'm saying the y label is component loss. Then I'm defining what is the font name and what is the font size. I'm also setting the like here, CGN font name. Yeah, I believe here it picked, like here it picks like not all the components, like I believe this is the title. Yeah, here. The thing is, on this figure, I want to create like what we call this, like annotation or something. So this annotation, if I put the annotation inside the for loop, every time it's gonna plot the figure, it's gonna put annotations. So you're gonna find like 100 annotations on top of each other. So I take them outside of the for loop, and I put them in the same figure, figure 2, plot, and then I call like the, I plotted them, like I made some of these curves a little bit thicker. The thing is, when we publish this in a journal, it's many curves. We cannot list the name of all these curves. So we take sample curves, like these 5 curves, and I made them thicker and I give them names so that anyone is reviewing is seeing some examples rather than having the 100 annotation. So I'm picking 5 of them and giving them special colors, and then I would give annotation for these 5 down here. That's like for publications. And then I said legends, oh sorry, it's called legends. So I'm putting the legends one by one here, okay? So all these are kind of the way, yeah, all these lines, sometimes we write more lines when it comes to plotting because we need to add more details, more colors, more legends, and all these stuff. All right. Figure 5, I don't think, okay, we might escape this too. All right, by the way, you will have to develop to write all this MATLAB code on your own. I'm not gonna give it to you. We're gonna watch the video. I'm scrolling step by step and go write it one by one and see how it's gonna progress with you, okay? That's one thing to do. Second thing, this part of the MATLAB code, maybe you don't have to write it, but if you wanna write it and see, because we're gonna do this approach in a different way right now. This is like a different way that it's not that good as the one that I'm gonna explain it later, but if you wanna write it and see what it's gonna get you, you can do this as well. I'm gonna skip this section and this section, and I'm gonna go to the probability of exceeding each damage state. Do you guys remember when we talked about how we can move from component level to building level? And I told you we're gonna group the components, but the thing is, we cannot take an equal average. We need to take weighted average because some components are expensive and some components are cheap. So basically, we have 5 curves, and these 5 curves, we need to make them one curve. So I said we can take the average of the 5 curves, like let's say, like you have this here, a component, and this is another component, and this is another component, this is another component. So you can take this value 1, 2, 3, 4, and then you take the average of them and get 1 point. And same thing here, and get another point. Same thing here, get another point, and draw one single curve. But the thing is, this has a replacement cost of $20,000, and this has a replacement cost of $500. So we shouldn't treat them the same. So we said that we are gonna say the total replacement cost of this damage state is $40,000. So we are gonna multiply this by $20,000 over the $40,000 because that's represent 50% of the damage state, okay? And we're gonna do this for the 4 components. So if you look here, I said I wanna develop a fragility function and I wanna find the value of the probability of exceedance at each of flood depths. Like I said, from J equal to 1 up to flood depths equal to 1,000. But 1,000 doesn't mean 1,000 meter. It's the value in the 1,000 cell. Like if you go here at D, actually it's 1,001. Why? Because we have a starting point. Like it's 1,000 value, but we are starting from 0 up until we go to 1,000. So, but they are 1,000 interval. Okay. All right. So we have from 0, and we are going 0.01, 0.02. So basically, you cannot say to MATLAB, I want to find the value from 1 up to 100 or up to 10 meter, because this is not the value of the depths. This is the value in the matrix. So I want to go from value in cell number 1 to the value in cell number 1,000 or 1,001. And that's what we're doing here. And if we go to the value all the way down, it's 10 at 1,001. Okay. And I'm starting with, I'm giving the MATLAB a starting point. Like I'm telling MATLAB, I'm starting from exceedance probability 0 for each damage state. Like damage state 0, 1, 2, up to damage state 4, all are zeros. Then I'm saying, like if you guys remember from the Excel sheet, these are the groups of the components, right? So I wanna group these 6 components into one group, and these 7 components or 5 components in one group, and these components in one group, right? So I'm taking them group by group to get one curve that represents them. This is group number 1 for K from 1 to 6, and component from 7 to 13, and 14 to 41, and 42 to 82, and 89 to 94, and finish all the groups. Okay, so for each group, I want to find one curve. This one curve is going to be damage state 0. For this group, it's going to be damage state 1. So how can I find the weighted average for this group? Look what I did. First, I start by 0. So here I put 0, and then I said it's equal to 0 plus the probability of failure of the component K. By the way, I'm making this for loop, so this is gonna be looping. Why I'm making it like this? This is because I said that I have 4. So the 4 is gonna do, I need the summation, right? I need summation for component 1, component 2, component 3, up to component n. And each value here has the probability of failure of component 1 multiplied by the replacement cost of component 1 over the total replacement cost of the whole damaged state, right? So that's for component 1, and that's for component 2, component 3, component 4, and then I'm gonna sum all of them. That's the weighted average. So what I did here, I made a for loop, so every time, look, I start with 0, so I put 0 here. Once you finish component 1, damage state 0 is gonna have the contribution of component 1, and then you are gonna end this loop and start again for component number 2, but here, the value here is gonna be the recent value that you already calculated. Like for component 1, this value. And once you finish this, it's gonna be summed on this, and once you finish this, it's gonna be summed on this too, and then the summation of all of them. So that's what is this for loop is doing. It's like a summation. So I did this for, you can do it in completely different ways, but I believe this is the easiest way to do summation in a MATLAB. Because we need to do summations. There is no way that I can do summation except that I have to do this. I have to start by 0 and then find what is the weighted average that comes from component number 1. And once I find it, it's gonna be in damage state 0. Then you are gonna loop and you are gonna start with the weighted average that come from component 1. And then you are gonna make another loop and you are gonna add component number 2, component number 3. And here, you basically multiply the probability of failure of component 1 at the flood depth J, and multiply it by the replacement cost of the component that comes from the matrix A over the total replacement cost. And look at this. This is the total replacement cost coming from at column number 24 from this Excel sheet. Do you guys remember when we had the Excel sheet? We had some columns at the end that has the mean of the all damage state, the mean replacement cost. So basically, I'm dividing the replacement cost by this value. Okay. So going back to the MATLAB code, I was able to find what is the XCNS probability of damage states 0, and I do the same thing for damage state 1, damage state 2, and damage state 3. All right, once you do it, I want to calculate what is I want to have one single curve. By the way, this is going to give you 5 curves. One for damage state 0, one for damage state 2, 3, 4, 5, and you finish. But what if I want to find not this? I want to find something like this, a loss function that has flood depths here and loss value here. How can I find this? There's an equation that basically I can multiply the probability of being in each damage state by the replacement cost of the damage state. What does that mean? All right, let's escape this part. Like, let's say that I understood how these damage state came from, and you were able to draw, like, let's say this is 1. Let's say you have another curve here, and this is 10, 5, 0. Look at this. If you want to find out from this curve what is the total replacement cost, so I mean, like, you want to have another curve like this, but rather having the probability, having the loss, and having the flood depth here. So for example, this curve is going to be something like this. How can I find this curve? All right, you need to find what is, let's say I want to find this point. From this point, you go up there. All right, I get what is the probability of being in each damage state. Like this is no damage, no damage. This is damage state 0, damage state 1, damage state 2, damage state 3, damage state 4. That is the zones of the damage. If you are here, that means there is no damage. But if you are here, there is damage. Okay, so you are gonna find what is this probability, what is this value, and 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 what is the value down there. And you multiply the probability of being in this damage state by 0, because if you are here, that means there is no damage. And if you are here, that means there is insignificant damage. Insignificant damage is maybe 0.01 or 0.02. You multiply this probability by the replacement cost of this damage state. Do you guys remember when we have all the components, and all the components are costing $10,000, $20,000, we sum all of them, and we get one value? If you multiply this by the total replacement cost of this damage state, and this value by the total replacement cost of this damage state, and sum all of them, you're gonna get one single number telling you what is the loss at this point. How we get this? Multiply the probability of being in each damage state, not the exceedance. Because the exceedance, do you guys remember the difference between the exceedance and being? Being is that you get this value and get this. But the exceedance is from here to here, the total. All right? Okay? All right, so we get these two values. How can I do this? I told you how to do it last time. By subtracting this from this. So that's what I did here. I said, get damage state 0 and subtract damage state 1 and multiply this by the replacement cost of damage state 1. And then 1 minus 2 and multiply it by the replacement cost of damage state 2. 2 minus 3, multiply this, 3 minus 4, and then multiply this, 4 minus, and then for the last one, you don't subtract it from anything, because look at this. For the exceedance is the same as the probability of being in a damage state, because you subtract like this from 0. Okay? But here, this one has one below it, so this minus this, and this minus 0. So the last one is damage state 4. You don't change it. That's what I put it here. And these values, 89, 7, 14, these comes from the Excel sheet here, as I showed you. This values. Sorry, it's the cumulative values. This values, and this values. The replacement, the total replacement cost of the damage state. When you go home and try to do this and do it by yourself and step by step, you are gonna understand what I did exactly. All right, so okay, so let's say I was able to get these fragilities. Once you draw these fragilities, like once you draw them, you plot them, you will find out. Can you see this dashed line?
Yes.
This is the fragilities that we got. Okay? But they don't look friendly. Like, look at this curve. It's like something like this and goes up and down, and like this, because that's the raw fragility, the one that we get from the data. The thing is, when we need to do analysis, usually we don't provide because the way that we draw this curve, we had 1,000 number. And this 1,000 value of X and Y, we connected them and we made this curve. When we take this to research, we usually fit the curve, make a best fitting of the curve. So the next step, after I found out the fragility, I fitted them to a log normal distribution. We usually fit the fragilities to log normal. And we have, rather than having 1,000 coordinates to draw them, we're gonna have only two numbers, logarithmic mean and logarithmic standard deviation. And we give this to MATLAB and we tell the MATLAB, draw the log normal CDF that has this logarithmic mean and logarithmic standard deviation. It's gonna draw this black curve. There's a function, I'm not gonna explain or get in depth like about this function. This function, it's called like log normal fitting, and it's called fit search, this one. So this function actually is the one that take the raw data from the MATLAB code and then doing some log normal fitting and then generate the log normal parameters and draw the updated fragility. Okay, I'm gonna give you this function, but I believe it's easy to write it. Like right now you have it. You just, the way that you do function, maybe search on YouTube how to develop a function. The thing is, there's some tools that are already in MATLAB, like the log norm, rand, or multiplication. This is already there, but there's some stuff that are not in MATLAB, so you have to create them on your own. So this function, I created a function. It's called function, and it takes these inputs x, c, f, c, and then do some fit search, and then it gets you d, and the depth was the probability of failure. Okay, so it takes input and gives you output, and do this process to give you the output. Right? I can give it to you, or you can develop by yourself. Once you develop it, you keep it in the same folder. And then let's get back to here. Yeah. If you look here, I applied the function. I give it like the inputs, and then fit search. That's the name of the function, and I give it the old parameters. And then it's gonna do this for the 5 dimension states. All right, and then I was able to redraw them. Like that's when I was like trying to redraw. And by the way, when you get new fragilities like these new ones, all right, I have my older fragilities are the one in the dotted line, and if you guys remember, I used them to get the loss function. But once you fit them, you are gonna get slightly different numbers. Like if I go here at 4, when you hit the dashed curve, it's gonna be different from hitting the solid curves. So you are gonna get a little bit or slightly different probability of failures. So your loss function is gonna be a little bit different. Okay, so that's why here I recalculated the mean total loss based on the new fragility parameters. Okay, and the next step is like I'm drawing some legend. I'm just like this one. I'm trying to make the fragility look much better. Maybe you go through like what I have done. I'm not gonna explain how I plot things because that's something that you can do on your own. Like see, that's what I did. I go to Google and say how to plot a curve, how to shade a curve, how to do something on a curve. So here I'm defining some colors, defining some annotations, and just to make the curve look like this. Look at this. Maybe I wrote, I don't know, maybe 100 line or maybe 50 line just to make this curve look like this. Just to like make this area look darker gray, lighter gray, more lighter, maybe up to white. So I have to define different types of gray, and I have to define these zones. Like I have to go point by point so that I tell MATLAB which area that is gonna get the gray number 1 or the gray number 2 or the gray number 3. Okay, maybe you go and then search how to do this. This is kinda, I don't know, like maybe it's important when you publish because you have to have a really good figures in the paper. So that's why I do this. But other than that, it's not like what we are doing, like science or basics or anything, right? Okay, so that's for the fragility. And let's say that we got this. Yeah, the last part here in this is it's a different approach. And this different approach, do you guys remember when I developed the 3D matrix that has for each flood depths, for each component, for each simulation with 0 and 1? I'm gonna do something different. That's a completely different approach, but not fragility. It's a loss method. But it was really interesting. Like when I did this, I thought about a different way. What if, rather than in this matrix, rather than putting 0 and 1s, what if I put losses for each component? Like what if I put loss value rather than 0 and 1? Because if it's damaged, that means it's 100% losses, so I lose all that money, right? Because if this component is damaged, and it's 100,000 value, so I'm gonna put 100,000 losses. So that's what I was trying to do here. I'm gonna find the component losses, and I'm gonna find it for each flood depth, for each simulation, for each component. If the damage matrix, the 3D matrix that we have, has 1 or more than 0, so pick a random number of the loss value of the component. Like rather than I generate 1,000 simulation, I pick one random number of the total replacement cost of the value. So, and we are gonna do this for each simulation. So rather than generating the simulation one at a time, like the whole 1,000, I'm gonna bid them one by one. And I'm gonna do them simulation by simulation and place them in the matrix, all right? So that's what I did here, and I said put an absolute norm rand based on the mean replacement cost and the sigma, which is the standard deviation. And by the way, I'm not gonna put 1,000 simulation. I'm gonna put only one simulation because I told you I'm gonna do them one by one inside this matrix. And then they are gonna be 1,000. When this full loop is done, I'm gonna get into this second loop. And at the end of the day, rather than I'm gonna have a 3D matrix of the damage, I'm gonna have a 3D matrix of all the component loss that has for each flood depth, for each simulation, for each component, there is a random replacement cost of the component, okay? And it's gonna be the same thing. If you take the mean of all the simulation, it's gonna give you the mean replacement cost of the replacement cost of the component. All right, since I have this, it's gonna be a 3D matrix. And the second step, rather than having a 3D matrix, I wanna convert it to 2D. And rather than having a 1,000 simulation of the replacement cost of the component, I can take their mean, like I told you, this component can be 1,000, can be 900, can be 1,100, can be 1,200, and they are all in the matrix. So rather than I having depths of the matrix, like let's say this is the 2D and this is the 3D. This is the flood depth and this is the component number. Like here. Here's the component number. And on the third axis is the depth. Something like this. So for every component, for every simulation, and for every flood depth, you are gonna have a value. Like this component has a replacement cost. Let's say this is gonna be flood depths 0.00, 0.01, 0.02. And then this is gonna be, let's say, 1,265. And let's say here 1,121 and 1,206, 1,567, whatever numbers that we have. So I want rather have 1,000 simulation, 1,000 number. Take the average of this. Once you take the average, basically you cancel this line. And then it's gonna be 2D matrix. Okay? 2D matrix that has component and depths like this. Let's say it's gonna be, let's put the depths here, depth, and here's the component, let's say component 1, component 2, 3, and depths 0.01, 0.02, 0.03, and then here you are gonna have the mean of the replacement cost of each component. So that's what I did here. I'm asking MATLAB to develop a mean and a standard deviation, and I'm taking the mean in the vector number 2 in the matrix. And what's that mean? The mean, look at here, this matrix has n depths, that's the vector number 1. And on y-axis is the number of simulation. And here is the number of component. I put here 2 because the simulation is in vector number 2. If simulation, if you set here 3, like if you put here 3, so it's gonna take the mean of the third vector. If you put here 1, it's gonna take the mean of the, so what mean that you wanna take? I wanna get the mean of all the simulation. That's why I put here 2, and it's gonna take the mean of all the component replacement cost. And then I plotted in figure number 91, that was the component replacement cost. It was 1,000 simulation, and this actually the average of them. It was something like this. That was a different approach of plotting the replacement cost, and I can do it for all the components. And actually, by the way, it is the same if you got these, like they are almost the same. The one that we got here is the same one that we got here. It was just different approach. All right, and at the end of the day, I was able to get the summation, like the summation of the component replacement, of all the component replacement costs. Like let's say I have this curve for the 94 components. So what I did, I take, like let's say I want to find that the replacement cost at depth equal to 4 meters. So I take all, by the way, if you take one section at each flood depth, you will find 1,000 simulation. Like if I take a section at flood depth 6 and you go up there, there's 1,000 point. And if you take section at 7, there's 1,000 point. And this line is the average of the 1,000 point. And this shading is +1 standard deviation and 1 minus standard deviation. So if you want to find the replacement cost of the whole building, you come at, like let's say at 6 meters and cut in all the figures and take the 1,000 simulation and sum each simulation together. Like you put, like let's say component number 1, simulation number 1, you are gonna sum this number with the other number for all the simulation, like for component number 2 and component number 3 and component number 5, and take the summation of the replacement cost at this simulation is gonna give you the total replacement cost of all the building. Okay? So you are gonna end up having something like this. That's the curve. This is the total replacement cost of all the building. And if you take one section, you are gonna find out 1,000 simulation. Each point represent the summation of the replacement cost from simulation number 1 for component number 1 plus component number 2, 3, 4, 5. That's simulation number 1. Then simulation number 2, 3, up to 1,000. You get the 1,000 point. Then I take the average and take the mean, and I get one single curve. So this approach is different from the approach here because this one is based on the fragility, but this one is completely direct from the component loss. And I plotted them, I believe, on top of each other. It gives me a curve like this. Let me zoom in. Look at this. The black one is the one from the approach number 2, like the one that comes from these points, and the blue one is coming from the fragility. Last question in this lecture. Do you know why this one is not matching this one? Why they are not on top of each other exactly? By the way, they have to be on top of each other because they are almost coming from the same data.
Because I made the log fit for the.
Because it's excellent. Because do you guys remember? They are not the raw fragility anymore. I fitted them. So when I fitted them, they shifted a little bit, but it's not exactly the same value. But if I use the non-fitted fragility to generate this curve, it's gonna be matching this curve exactly. But because I fitted the fragility and it changed them to make their shape look much better, so it gives me a little bit of different curve. This one is the fitted fragility, but this one is coming like from non-fitted data, like the fitted exactly the same data. And by the way, this curve is the one that used by hazards, like the one that used like what the US used to account for similar buildings. And if you find that, like if you look, you will find that they are almost maybe matching until here, but here they don't match. And this is because the hazards doesn't consider building can get a complete damage. Like they say, if even a building is submerged with water, the structural system can be salvaged, like you can't use it often. But here we assume that all the building can get to 100% damage. So that's why they don't match at this part, because we consider that the building can get 100% damage. Here, building didn't get 100% damage, like maybe maximum is 60 or 70%. All right, so that's it for now. Here's the rest of the code. Like I'm just like, because I'm recording the screen, all what you have to do when you watch this on YouTube, you go through the code line per line and try to write it. It's around, maybe once you exclude the parts that we don't need, maybe it's gonna be 300 line or 250. So try to go through it, start to write it, because this is gonna be part of the project that you have to present at the end of this class, along with other things. So I would recommend that you guys start writing this code right now, so that you don't waste your time. And I believe that's it for now. Next time we are gonna see what applications that we are gonna have, right? I might send you guys, you're gonna use the same code, but I'm gonna give you every one of you different archetype to do the same thing. Because at the end, when you guys present your project, I wanna see how every archetype shows with you. So what I'm gonna do, I'm gonna upload, we have 10 in the class, I'm gonna upload 10 Excel sheets for 10 different models that has 10 different components, but it's gonna be the same code. It's just different number of components. All what you have to change, do you guys remember in components? The in components in one archetype is gonna be 90, some archetypes is gonna be 64, so that's the thing that is gonna change, right? And also the damage states. Do you guys remember damage state 1? So it's gonna have different groups, okay? I'm gonna show you next time what you are gonna do exactly, all right? Okay, see you guys on Thursday.